Up section 1.3, and the first thing we're going to look at is what's called the greatest integer function. Well, first of all, as the name says, this is a formula that, or a function, whenever you plug something into it, the answer that you get back is an integer. Specifically, what integer? It's the biggest integer you can think of that's less than or equal to the number you plugged in. So the biggest integer you can think of that's less than or equal to the number you plugged in. So let's say I said to you 4.2. If you took 4.2 and filled it in right there, what's the biggest integer that you can think of that's less than or equal to 4.2? Yeah, 8?
4.
4. Yep. How about 4.3? What's the biggest integer less than or equal to 4.3? Yeah, Alex?
4.3 is less than or equal to.
Biggest integer less than or equal to 4.3?
4.3.
That's not an integer though. It's gotta be an integer. Yeah.
4.
4. Yeah. How about the biggest integer less than or equal to 4.5? Yeah.
Then 5.
Is 5 less than 4.5?
Oh, less than or
It's got to be less than or equal to whatever you plug in.
4.
4. How about 4.7? We good for that? Yeah. 4. How about 4.9? Still 4. 4.999. Still 4. 5. What if I plug in 5? Now I get 5. So all of a sudden it jumps. Okay? If you plug in anything that starts with a 4, doesn't matter what the decimal is, you get a 4. Once you get to 5, all of a sudden it jumps up. Because it jumps, it kind of looks like a set of steps. So sometimes this is also called a step function. Right, let's look at it, for example, plugging in a 2. If you plug in 2, you get 2. 2.1, 2. 2.5, 2. 2.8, 2. 2.99999, 2. When you get to 3, you're not here anymore. That's why it's an open circle. When you get to 3, it jumps up to the next step. That's why that has a closed circle. You can graph that on the calculator. The notation that you're seeing with the double brackets, that's what our book uses. The calculator uses that INT. Okay, I'm going to show you where that is. So if you go to on, go to y equals, clear out anything else that's in there. And to graph the integer function, or greatest integer function, press math. Press the right arrow to go to number, and it is the 5th option down. It is lowercase on the calculator. Some have it capital, our calculator doesn't. So it's math, go to number, and then it's the 5th option down. Then you just have to put in an X. And whenever a parenthesis is opened, either automatically or by you, you should close it. So if you type in int x and then do zoom 6, you'll see exactly the same picture. Not as detailed as mine. It doesn't have the open and closed circle, which that is kind of important to understand what's happening right on the edge of the step. But you can still see the general look of the function. Now, let's think about like negative 2.3. What's the greatest integer you can think of that's less than or equal to negative 2.3? If you get stuck thinking about it, remember, less than or equal means if you had a number line, you need to give me an integer that's to the left of negative 2.3. The first one you come to. That's the biggest one. Yep.
-3.
-3, yes. if you did I meant to put negative 2.3, that would give you negative 3. That's a decimal point. Yep. Now, let's look at that and see if we can figure out these two things. The domain and the range. That's going to be example 7. I think I already said that to you. It's also called a step function because it looks like a series of steps. Okay, so find a complete graph. I already did that with you on the calculator. The standard window, zoom 6 is good. But now let's see if we can get the domain and the range. What numbers, or what kind of numbers are you allowed to fill in right there? And if you're not sure how to answer that, try to think of the opposite. Is there anything you're not allowed to plug in? And that should help you figure out what you are allowed to plug in. Okay, so what kind of numbers would I be allowed to fill in for x in the greatest integer function? Yeah?
All real numbers.
All real numbers, yeah. Remember, domain is how far left and right the graph goes. The graph goes left and right forever. And every single value is hit, right? Even though it looks like there's gaps, there's an open circle on one end of the step and a closed circle on the other. So every value left to right is covered. So that's all reals. Now, the range is up and down. How far up do those steps go? If we could zoom out forever. Yeah. They go up, yeah, it goes up forever. And how far down do the steps go? Yeah. They also go down forever. So does that mean the range is all real numbers? No, not in this case. Just because this graph goes up forever and down forever, it does not mean the range is all real numbers. The range is the answer that you get back from this function. There are certain kinds of numbers you will never get back as an answer from the greatest integer function. So what would be the range then? Of the greatest, yeah, Aiden?
All integers?
Right, all integers. You will never get back a decimal. Okay, so the range is all integers. That's just a special function, nothing particular about it. I just wanted to go through. Let's look at this one. So, same as the last one, graph it and find the domain and range. 16x minus x cubed. If I haven't shown you how to do an exponent yet, let me show you that right now. To do an exponent that's not a 2, because you can do 2 with the button right next to the comma on the left side. But we want to do a 3. So right below clear and above the division sign on the right is that up arrow. If you press that, now your cursor has moved up to the exponent, and you can put in a 3. Yes? Yeah, just sign up for me. Now, I don't have to type anything after that exponent of 3, so I'm done. But let's say I had to type in something else. If you keep typing here, your cursor is going to stay in the exponent. Well, if you're done with the exponent and you don't want to be in the exponent anymore, you just press the right arrow and it will get you out of the exponent. Now if I start typing, it's regular numbers again. Okay. I don't have anything else I need to type, so I'm good. Let's do zoom 6. The directions are to find a complete graph, meaning we can see everything that's important. Do you think zoom 6 gives me a complete graph? No, not quite. We're going to learn a little bit more eventually, but when you are graphing a polynomial, if you subtract 1 from the biggest exponent you have, technically there's an exponent right there as well, but the biggest one is right here. If you subtract 1 from that, you get a 2. That 2 tells me the number of times this graph can turn on the screen. It's not a guarantee that it does turn that many times, but it's a maximum number of times. This graph is turning off the screen. So I need to see those turns, okay, to get a complete graph. What do I need to adjust on this window in order to see higher and lower? Yeah. The Y min and the Y max. How much higher and lower? Well, you could play with it, but I just know that negative 50 to 50 is going to end up working well. Leave everything else the same. Now, you have a complete graph. Right, so the first part of this problem, find a complete graph. I would write down that window. Negative 10 to 10 for the x, negative 50 to 50 for the y's. All right, last thing they want is domain and range. Domain you should be able to do without a calculator. There's 2 things that can mess up the domain. One of them we actually talked about in the homework. It was number 18. What's one thing that you want to make sure you don't do in a function? You want to make sure that you never divide by 0. That'll never happen here. To divide by 0, you'd need a fraction in your problem with a letter in the bottom. There's no fraction in this problem. So you never have to worry about dividing by 0. But there is one other thing you've got to be careful with, and we talked about it last week. Because of the types of numbers we're dealing with, we never want to do what else? Yep.
Negative square root.
Right, we don't want to take the square root of a negative. That's not a problem here either because there's no square root symbol. So the 2 things that could give us a problem are not here. So what does that mean the domain is going to be? Yeah.
All reals.
All reals. Okay. Which you can write this way or this way. The lowest you can go is negative infinity. The highest you can go is positive infinity, but you can't include either one. So that's 2 ways of saying the same thing. Okay, range. That's the one that's a little harder. We need the sketch. The range is how far up and how far down the graph goes. Looking at the formula, how many times did I say this graph could turn on the screen? Yeah. It said it could turn twice. Can you see both of the turns on the window now? Yes. Then the graph is not going to do anything else to turn. It's going to continue the same behavior if you zoom out. It's just going to continue in those 2 directions. So, based on that, what do you think the range would be? Nick?
I have a question about something else. How did you figure out how many turns it's going to have?
I subtracted 1 from the highest exponent.
Okay.
And we'll learn when we study polynomials. We're gonna learn a little bit more about that kind of stuff. Yeah. This number, another way to think of this number is it's the maximum number of times it can cross the x-axis. 1, 2, 3. 3.
Okay.
So that's another way to think of that number as well. Yeah. Yeah, the range is also always, right? The graph goes up forever, it goes down forever, and it doesn't do any kind of jumps like a step function. It's continuous, it's connected the whole time. So it will hit every single number from negative infinity to positive infinity. So always. Any question on that? Now, just to take this one and show you something, I told you that that 3 is the maximum number of times it could cross the x-axis. Well, if you look at this one, I got to go a little bit higher so you can see it. Notice this time, just because it has a 3, it doesn't actually cross 3 times. I shifted it up, so now it only crosses once. Okay? So this 3, it's like a maximum, but it's not a guarantee that it crosses all 3. This time it's just once. Still turns twice. 2 times. So knowing what these exponents do, they give us hints at what we're looking for when we're drawing it. So that's a lot of what we're going to learn as we study. Each chapter is like its own function in the first 6 chapters. All right, let's look at this problem. So it says we have a rectangular pool, and they give us the dimensions of it. It's 30 feet by 50 feet. There is a sidewalk around the pool, and the sidewalk is the same shape. It's a rectangular shaped sidewalk right around the pool. And the width of the sidewalk is the same. It's X feet wide all the way around. Now, we don't know the width of the sidewalk. That's going to be what they want us to find. But we do know the surface area of the sidewalk is 600 square feet. So knowing the dimensions of the pool, the fact that the sidewalk is uniform all the way around, and the area of the sidewalk, that's enough information to piece it together and figure out the width of the sidewalk. So what do you think, with all that information, we've talked about different approaches we can use to solve problems. What approach do you think would help us to see what's going on in this problem? What problem-solving approach does this really lend itself to? Yeah?
Maybe like creating a visual?
Yeah, absolutely. Creating a visual. Yep. So we want to draw this out. What is something that's going to be in our picture? Something from this information. Yeah? Okay, yeah, we're going to need a rectangle for the pool. So let me draw that. Okay, so there's our pool. And why another rectangle? What's that for? Yeah?
The sidewalk.
Yeah, the sidewalk around the pool, and try to make it uniform as we can. Now, they told me the pool dimensions. I'm going to need someone to remind me. What were the dimensions of the pool? Yeah.
30 feet by 50 feet.
30 feet by 50 feet. Okay. So we've got the pool, we got the dimensions. What else did they give me in the problem that I need to label in the picture? Yeah.
The area of the sidewalk?
Okay, I'm going to write that off to the side. I'm going to call that A sub S. S stands for sidewalk. And what was the area of the sidewalk? 600. Anything else that I need to label in my picture? Yeah.
Maybe you could do the area of the pool.
Okay, so that's not something they gave us, but it's something we can derive from what we were given. So we do want that for later on. And what is the area of the pool?
1,500.
1,500. Yep, 30 times 50. So that's important. Anything else that they gave me that I have not labeled there yet? There is something else they gave us. Doesn't have to be numeric information, just has to be information. Yeah.
Was it with X?
The width of the sidewalk is X. Yep. So that's X on that side. That's on all the sides. Okay. The sidewalk has a width of X. Okay, so now we've labeled everything they gave us. We even figured out something that they didn't give us. And now we got to somehow find the width of the sidewalk. First thing we're going to have to do is come up with an equation. We'd like to come up with an equation that starts with the area of the sidewalk. Now, pretend that this big rectangle was like a piece of paper. And I said to you, here's the big rectangle. I want you to give it back to me, and all I want is this sidewalk showing. I don't want anything else. If I gave you this big rectangle, what would you do to it? To have just the sidewalk and nothing else in the big rectangle, yeah?
Take out the middle.
Cut out the pool, yeah, cut out the middle. So if we're going to cut out the pool and get just the sidewalk, what arithmetic operation do you think cutting out the pool would have to do with? Add, subtract, multiply, or divide?
Subtraction.
Yeah, so we're going to subtract out the area of the pool. What are we going to subtract out from? The big rectangle. Just call that A sub B. There's the formula we're going to create. The area of the sidewalk is the area of the big rectangle with the pool cut out. Now we have to fill those three things in. Either with stuff we were given or with something we have to calculate. Area of a sidewalk, were we given that information? If so, what is the area of the sidewalk? Claire?
600.
600. Were we given the area of the big rectangle? No, that's not something we were given. But we know it's a rectangle. And what's the formula, William, for area of a rectangle?
Length times width.
Length times width. So leave some space. We're going to have to find the length. And then we're going to have to find the width. Now, sometimes at this step we have to figure out the area of the pool, but we already did. It's 1,500. Okay, so we got to figure out the length and the width of the big rectangle. Well, the length, I'll give you a hint, if you break it into pieces, it makes it easier to find. Part of the big rectangle goes from there all the way to there. So you have that part. Then you also have a part from here to here, and another part from there to there. So anyone think they know what the expression would be for the length of the big rectangle? Yeah.
50 plus 2x.
Yeah, 50 plus 2x. It's the pool plus the sidewalk on each end. And the sidewalk is doubled because there's a sidewalk on each end of it. So 50 plus 2x, you could also say 2x plus 50. I'm just going to do it that way. And in a similar way, anyone can tell me the width of the big rectangle? Yep.
2x plus 30.
2x plus 30. And now we need to do that out and solve for x. And that will be the width of the sidewalk. Okay, so that's a binomial and a binomial, so we need to use FOIL or double distributive. What's 2x times 2x? That gives me, how much? How about Jake?
2x times 2x equals 4x
4x squared. Now multiply your outer and inner. How many x's are we going to get when we do that and then combine them together? Yeah, Meg?
Is it 160 X's?
160 x's, yep. And then the last part is 50 times 30. We already did that earlier. That's 1,500 minus 1,500. Okay, what's going to happen now on that line?
We can eliminate the 1,500.
Yeah, the 1,500s are going to cancel. And now we're left with this equation. What kind of equation is that? Yeah, it's a quadratic, exactly. Whether we're going to solve a quadratic with factoring or quadratic formula, or even completing the square, a good first step is to get it equal to 1. Yeah?
Can I go back?
Yeah, just sign up for me. Nick?
To 0?
Yep, let's get it to 0. So I'm going to put everything on the right side. Okay, so now we've got it equal to 0. Before we jump into the method, either quadratic formula or factoring, we're going to do something to make the numbers a little easier to work with. What? Anybody see what you could do here? This doesn't always happen, but it does with these numbers. Yep.
5 by 4.
You can divide everything by 4. Is it necessary? No. But it will make everything a little easier to work with. Now, that's not factorable using integers. So we are going to have to use quadratic formula. Okay, let's start with the easy question. The quadratic formula has 3 letters in it, 3 variables. What are the names of the 3 variables that we use in quadratic formula? Yeah. A, B, and C. Can anybody tell me, looking at the equation, what A is? Yep, go ahead.
X.
So A will have to be a number.
Oh,
1. Yep. A is 1. How about B? Yeah.
40?
40. And C? Yep.
Negative 150.
Negative 150. As easy question. Now, I need the quadratic formula. How does the quadratic formula start out? What's the first thing? Yeah? Yeah, go ahead.
Negative b.
Negative B, yep. Let me scroll down a little bit. I'm going to put it up here in its own little box. Yep. Starts out negative B. Okay, and then what? Yep.
Plus or minus
Plus or minus
the square root.
the square root. Okay, good so far. What's the radicand? What goes under the square root? Yeah, Dave.
B squared minus 4ac.
B squared minus 4ac. Perfect. Can somebody else give me the denominator? Yes, go ahead, Malachi.
2a.
2a. Yep. So now it's just a matter of filling in the a, b, and c and see what we get. So we get negative 40 plus or minus square root of b squared. 40 squared is 1600 minus 4ac. Oops. 4 times a times, I meant to put c. 4ac is negative 150, all divided by 2 times a, which is 2 times 1. Now, let's look at just the radicand. 4 times 1 times negative 150. When you multiply those 3 things together, that's a negative, and you're going to be subtracting a negative. So what happens when you subtract a negative? Yeah.
Turn into a positive.
It's going to turn into a positive. So might as well just handle that right now. That's going to be a positive. What's 4 times 1 times 150? Yeah,
600.
600. I'm just going to put that up above it. So that's 600. So that's going to help us simplify a little bit. Negative 40 plus or minus. What's 1600 plus 600? Yep,
2200?
2200. All divided by 2. Now we just have to put that in and see what we get. Well, let's type it in. Okay, the way I type it in, I generally do the top first, get the answer, and then hit divide by 2. So we got negative 40 plus square root of 2200. Hit enter, that's the top. And then I'm going to divide by 2. 3.45. That's my first answer as a decimal. Now, quadratic formula, when you're solving a quadratic, will generally give you how many answers? Yeah? 2. So does that mean our sidewalk could be 2 different widths? No. Since this is a word problem, there should not be 2 different widths for the sidewalk. It's 1 width. Watch what happens if we do negative 40. Now do minus the square root of 2200. Okay, I don't even need to divide that by 2. We can just stop there and rule that answer out. How come? Yeah.
You can't have negative distance.
Right, we can't have that negative distance, that negative width. Is it a problem? Is it a solution algebraically? Absolutely. Is it a solution in the context of the word problem? No. So the width of the sidewalk is 3.45 feet. Okay. So any questions on solving that? Yes.
Is it that one?
Yes, just say up for me. All right, so I reviewed a little bit with quadratic formula and just kind of getting used to creating an equation that you weren't given using information from the word problem. Okay. All right, so 2 things left. Second to last thing is projectile motion. Projectile motion basically is a formula you can use that approximates, the height of an object that travels either straight up and straight down or even in like an arc, like if you're throwing like a ball or something. And the left-hand side represents the height. The right-hand side is the formula to find the height. So S sub t is the height. S of t. That's how you'd say that. Now, the height depends on a few things. First thing it depends on is gravity. That's what that negative 16 is. If you do this in physics, you might see a different number there. It depends on the units you use here. Since we're using feet and seconds, we have to use negative 16. That's what we always use. Okay, so first part is negative 16t squared. The next part, plus v sub 0 t. V sub 0 is the initial speed that the object is thrown at. So if it was like a ball you're throwing, the second it leaves your hand, how fast is it going? And the last thing I need to know is what was the initial height when you release the ball or object, whatever it is. If you're throwing an object, it's probably close to your height when you release it. If you were standing on a building, it would be your height off the ground. So whatever the initial height is, you plug in right there. So whenever you're doing a projectile motion problem, the first thing is to create or fill in this equation. I think it's a little easier than the swimming pool problem because you don't have to figure out the formula yourself. There's the formula. You just have to fill in two numbers. Initial velocity, initial height. Okay, so this says that a model rocket is shot straight up from ground level with an initial velocity of 64 feet per second. And there's two questions they ask us. First question is, what time does the rocket hit 50 feet? Okay, before we can even answer that question, we need an equation with that information in it. Okay. Anybody think they can give me my equation for the projectile motion in this problem using the information that they gave me up above? Anyone? Well, what does the equation start off with? Yeah.
Negative 16 t squared.
Yep, nothing to fill in there. Negative 16 t squared plus what would come next? Yep.
Plus 64t.
Initial velocity times time plus, and what's the very last thing in the formula? You don't have to give me a number, just tell me what it is. Yep.
It's the initial height.
It's the initial height. What's the initial height in this problem? Yeah? Yeah.
Zero.
0, right? Ground level. Okay, so now we've got the formula that we need. Okay. What time is the rocket at a height of 50 feet? If I was going to do this algebraically, where would the 50 get plugged in? There's two places, the independent variable or the dependent variable. Which one? Yeah?
Dependent.
It's the dependent, it's the height. So you would do 50 equals negative 16t squared plus 64t, and you would solve that as a quadratic, just like we did the pool problem. Okay, this time I'm not going to solve it as a quadratic. Okay, I'm going to do something a little different. Let's bring up the calculator. And did we do intersections on the calculator last week?
Yeah.
I think we did, yeah. Let's put 50 in y1. And let's put negative 16t squared. You have to use x. Negative 16x squared plus 64x in y2. Now remember, this is a horizontal line at 50. So I need to go to at least 50. I'm going to go a little more. I'm going to go to let's go to 80. So on your y max, oh, I could probably even leave it at 100. That's probably fine. The independent variable is time. Time has to be what kind of number? Yeah, go ahead.
Positive.
Yeah, it has to be positive, right? You can't, or 0, you can't have negative time. Now the dependent variable is height. What kind of number does the height have to be? Yep.
Positive.
Also positive, or 0 if it was right on the ground. Doesn't make sense to look at a height of negative 50. So let's set that as our window, and let's graph it. There's my line at 50, and there is the height of my object over time. Why does my object look like it's hitting a height of 50 twice? How can the object hit 50 feet 2 different times? Yeah.
Because it hits it the first time when it's going up, and then when it comes down, it hits it again.
On the way up and on the way down. So what I want to do is find the intersection point. So second calc intersect. Now the first time you hit enter, it just has to be a point anywhere along the blue line, doesn't matter where. and you hit enter. It should now say second curve. I'm past 5, which is way down off the screen. I want to see my cursor, just press left until you bring it back onto the screen. It doesn't matter where you click on the red curve. You just have to click somewhere on the red curve and hit enter. Now, the guess matters. The reason the guess will matter is because there's 2 different intersection points. You need to put the guess closer to the one that you want. Okay, I'm going to do the one on the right. Doesn't have to be exact, it just has to be closer. If you guys can move your cursor closer to the one on the left, we can also get that one. Okay, so you move it closer to the left, and I'll keep mine closer to the right. Once I have my guess where I want it, hit enter. And on the way back down, my object hits 50 feet at 2.94 seconds. That's on the way back down. Okay. How about on the way up? Did anybody figure out when it hits 50 feet on the way up?
1.06.
1.06. And again, to do that, you just do second calc intersect. Put it anywhere on the blue, put it anywhere on the red, but move your guess closer. It doesn't have to be right on it, it just has to be closer. 1.06. Perfect. Okay, so that's the first question. Okay, same graph, but this time I want to know when the rocket reaches its maximum height. When it reaches its maximum height, and then what is the maximum height? I want both. Does this have to do with the red or the blue graph? Which one? Yeah? Red. Has nothing to do with blue. Okay. Has to do with the parabola. So you're going to press second, and you're going to press calc, and you're trying to find the maximum height. You're not going to do intersect this time. Anybody have a guess which option would help us here? Yep.
4.
4, maximum. Now, it's similar. You're going to hit enter 3 times, but you have to put your cursor in the right spot. First of all, my cursor right now is on the blue line. That's no good. I need to be on the parabola. If you're already on the parabola, you're all set. I'm not. Hit the up arrow or the down arrow, and it will switch your cursor to another curve on the screen. Now, I'm past 4, which is somewhere down here. So if I hit my left arrow, now you can see my cursor on the screen. You need to be able to see your cursor. Because when you do second calc maximum, the first thing it's going to ask you for is left bound. Left bound means pick a point somewhere that's to the left of the maximum. Okay, so you've got to move your cursor somewhere to the left. It can be anywhere to the left, it just has to be somewhere. And you hit enter. Now the next question it asks you is, what is the right bound? Move your cursor somewhere to the right of the maximum. Okay, I know the maximum is right here. So anywhere to the right will be good. Hit enter. And what I've done now is I've given the calculator kind of an area to look at. The guess doesn't matter. You can put the guess anywhere you want. That's not right on where it should be, but it doesn't matter. Now, sometimes you get like 2.0000002, or some of you might have got like 1.9999999. Did anyone get that? 1.9? It's basically the same thing. The calculator is just doing an estimate. If we round it, after how many, or at how many seconds does the rocket reach its highest point? 2. It's at 2 seconds. And then what is the maximum height the rocket reaches?
64.
Yep. So we're going to be able to interpret each of those numbers. So max height is 64 feet. And this happens at 2 seconds. Okay, so maximum is another feature we use on the calculator quite a bit. Any question before we look at the last thing? Okay. So the last thing is called a piecewise defined function. It's just a fancy way of saying graph two things at the same time. That's all it is. So in a piecewise defined function, you have two different formulas that are working together to make one picture. That's a piecewise defined function. Two or more formulas working together to make one picture. And the way it works is that, let's say I had two formulas. I might use formula 1 if you give me a number less than 0. And I might use formula 2 if you give me a number more than 0. Maybe like ticket prices to a concert. If you're under 18, I use this formula to find the price of a ticket. If you're greater than or equal to 18, I use a different formula to find the prices when you buy tickets. So you generally split the domain into several parts, and you give a formula for each part. Like this one. This formula splits the domain into two parts. Numbers that are below 1 and numbers that are 1 or higher. So between these two, everything's covered. You couldn't give me a number that wouldn't fit either this or that condition. If you're thinking of a number in your head, it's either below 1 or it's 1 or higher. If the number you're thinking of in your head is under 1, you would fill it into this to calculate the answer. If the number that you're thinking of is 1 or higher, you would fill it in to that to get the answer. Okay. So all I want to show you is how you graph that. So it's two graphs working together to make one picture. Two different formulas. It's very similar to graphing any other function. We're just going to have to use some parentheses when we type it in. So let's type in the first one, 3 minus x squared. But when you type it in, put it in parentheses, just like this. Now the other thing I need to tell the calculator is when to draw it. I only want to draw that when I'm less than 1. So we have to put this in right next to it. Put a parenthesis. Put an x. Now I have not shown you where the less than sign is. I need to show you that. To get the less than symbol, you press second math. Second math. And you'll see a list of all the inequality symbols. We want the fifth one. So that's the first one. Now type in the second one. Put a parenthesis. X cubed. Make sure you hit the right arrow after you do that exponent, so you're not in the exponent for the minus 4x. And then we're going to graph that when x is greater than or equal to 1. So press x. Remember, inequality symbols are second math. This time you want the fourth one. Okay. That's how you type in a piecewise defined function. So you're going to see a blue function up to the number 1, and then the red function is going to take over after the number 1. So I'll do zoom 6 so you can see. There's the blue function. This part shouldn't be here. There's nothing I can do about the horizontal part. It's the blue and the red part is what you should be focusing on. Let me just make that a little bigger so you can see it. And pretend that this part is black. You can't see that colored part. That's a piecewise defined function. It's the blue one right up until the number 1. And then for the first one, was it a less than or equal to?
Why don't you spell an error? When I'm trying to do it.
All right, we'll take a look. Was it a less than or equal to on the number 1? It was just less than? Then technically we should have open circle. And then for the part that was 1 or higher, was it a greater than or equal to 1? It should be a closed circle. That's what a piecewise defined function looks like. It's just 2 different parts in the same picture. Okay, and if anyone had trouble drawing that, I'll come help you right now. That's it. It's a piecewise defined function. So the homework is just page 31. Okay, there's nothing on page 42 tonight, so it's just the problems on page 31.